At the end of 2019, one of the brightest stars in the sky, Betelgeuse, started doing something peculiar. It dimmed its brightness by about 40%. Now this is of particular interest because Betelgeuse is what we call a red giant. This is a star very near the end of its lifetime that once it reaches the end will die in a spectacular core collapse supernova. So this bizarre behavior from a red giant sparked a lot of interest, suggesting that it might be getting close to the end and would have something spectacular go off in the night sky very shortly. Well, astronomers looked at these claims and of course were hopeful that it was going to blow up, but you need to test everything, so they set about trying to understand what exactly was happening with Betelgeuse. So astronomers did it the way we know how, by taking images and spectra of this very interesting star. The first thing that astronomers did was take a very detailed image of Betelgeuse. Now Betelgeuse is very close to the Earth, and it's actually one of the few stars that you can easily direct image, meaning that we can take an image from a telescope on the ground that shows us more than just a point of light. We can actually resolve the star, see details on the surface of the star. And astronomers did this using the Very Large Telescope in Chile, in particular the SPHERE instrument mounted on one of the VLTs. And this image showed something quite interesting. The surface of Betelgeuse hadn't dimmed evenly. In the bottom half of Betelgeuse in this image, it's much fainter than the top half. Now this could suggest a number of different things happening with the star. Perhaps there is some weird convection going on which has made part of the star dimmer. Perhaps there's some kind of temperature contrast going on, which has also given the appearance of the star dimming. But it's not enough to conclusively say what's happening with the star, nor is it enough to say it's definitely going to blow up in the near future. So the other thing astronomers can use, which is an incredibly powerful tool, is to take a spectra of Betelgeuse. Now you can think of spectra as splitting up the rainbow of light coming from an object into all of the many different colors and measuring the intensity of light at each color in the rainbow. And the really cool thing is, each part of the rainbow corresponds to different atoms or molecules out in the universe. They each have their own unique fingerprint that you can associate with that atom or molecule. There are lots of things that you can do with stellar spectra, but one of those things is measure the temperature of the star. And the way you can do this is by fitting a black body distribution to the spectra. Now this gives you what the peak temperature of the star is, because in general stars can be treated like emitting black bodies if they're hot enough. But the type of star that Betelgeuse is, this red giant star, is actually too cold to be a black body emitter. It's got lots of complex molecules that exist in its atmosphere which complicate the spectra and doesn't give you a nice black body spectrum. So you need to be a bit more clever with how you measure the temperature of red giant stars. And one way to do it is to look at the depth of absorption by a particular molecule in the spectra, the molecule being titanium oxide. And in these spectra of Betelgeuse, one taken in 2004, the other taken in 2020 in February, showed that the absorption of titanium oxide is pretty much the same between these vast different times. And if you do some fitting to stellar models, you'll find that the temperature of Betelgeuse in 2004 is about 3,650 Kelvin, which is pretty warm but kind of cold for as far as effective surface temperatures of stars go. And in 2020, the temperature of Betelgeuse was 3,625 Kelvin. So its temperature was reduced, but it was only reduced by about 25 Kelvin, which isn't enough to explain the drop in brightness. So from the spectra, we could determine that it wasn't actually changes in the star that was driving this drop in brightness. So it needed to be something else. And to explain this drop in brightness, we need to come back to the idea of imaging Betelgeuse. If instead of looking directly at Betelgeuse, you look at the surrounding environment in infrared light, so that's looking at warm molecules that exist around Betelgeuse, you'll find something quite interesting. There's a whole bunch of debris and dust sitting around Betelgeuse. And this stuff will orbit around and move around Betelgeuse, creating a kind of dynamic environment. And the reason that this stuff is there is when stars like Betelgeuse get to their red giant phase and become very large, they become quite unstable and erupt enormous quantities of material out into space. So what the speculation is, by combining all of this information, is that you have a big chunk of dust kind of moving in front of the disk of Betelgeuse. Like in this image that was taken by a sphere, it's blocking the bottom half of Betelgeuse. Now this will reduce the total amount of light that reaches us here on Earth, because a lot of it will get absorbed and scattered by the dust surrounding Betelgeuse. Now of course a prediction to see if this is true is to say that the star should increase in brightness fairly soon. And fortunately enough for this model, that proved to be true. Betelgeuse is increasing in brightness again. So through all of these different methods of combining data and analyzing the physics of what's going on in this red giant, astronomers were able to piece together a picture of not the star changing, but the entire environment around the star changing and evolving in a very dynamic way. So unfortunately this means that, for now at least, Betelgeuse isn't on the verge of imminent death, but I guess be hopeful that one day soon it may blow itself up.